Hello, and welcome to this Intelligent Light webinar, Speed Up Production CFD with Extract Workflows. My name is Shane Wagner. I'll be your host. And all for coming. Let's begin. Most of you will know Intelligent Light as the people who develop, sell, and support FieldView. We've been doing that since 1990. We've been supporting the Visit LibSim since 2014, and a large part of what we'll discuss today is how we are bridging CFD and IT for our customers. And a lot of what we'll cover today is about the impact of your IT environment on your CFD workflow. So what we'll discover today: opportunities to break through limitations caused by the impact of CFD results files, low performance and high cost, what extracts are and how to use them, and specifically related to unsteady calculations, remote HPC resources, large size models, optimization, and design space exploration. And we'll also look at how extracts workflows can help you. At this point, it's my pleasure to introduce Steve Legensky. He will be our speaker for the rest of the event. And again, thank you for coming. Take it away, Steve.
Oh, thank you very much, Shane, for that great introduction. And thank you all for taking time from your busy day to join us for this webinar. I hope it will be worth your time. As Shane mentioned, I'm Steve Legensky. I'm the founder and general manager of Intelligent Light. Intelligent Light predates FieldView, so I've been here in this spot since 1984, quite a while. And what we're going to do is start this discussion, the motivation of it, by looking at the tradition and traditional characteristics of CFD workflows. So I chose some historical pictures for my first slide there, a Cray computer and also a removable disk drive. Typically, the space of CFD solutions that you can consider have always been bounded by practicality: meshing, solving, and getting compute time, and of course the schedule, how much time you have to get things done. And part of our consideration today is how you can get more things done within those limitations. The products resulting from this effort are results files, and everyone knows that. The post-processing step consumes the results files in the analysis step, where you get the payoff from your work. To further increase productivity, we can add automation and scripting to the mix, where you use automation to save time and effort on things that are repetitive. So you can use scripts to submit parameter sweeps, control many jobs, move results files around, and capture and repeat post-processing steps. And this can standardize the products that you get. So there's two parts to this really. Is the scripting can help you do things repeatedly without having to take all the time to do them manually. And furthermore, the products that you get become standardized. That is, a given script generally generates the same set of components within an image, an animation, or a report. The standardized plots of movies, besides leveraging scripting, can also help because decisions that are made on the content are actually easier to be made if people are looking at standard plots when they come to a meeting. So for very many years, especially in the automotive industry, these kind of standard plots, when you're going to review a design or talk about proposed changes, give everybody a common working format to understand things and to make decisions. And it also, by enabling a standardized workflow, it lets you encapsulate knowledge from, say, a methods group and distribute that to others. So practitioners can decide these are the kind of views or cuts or variables or isosurfaces, what have you, that are important to represent a solution, and then that becomes propagated throughout your organization. And it's good for many applications. I've got three examples here. If we start from the top right corner, we've got 6 different high lift wing cases with different angle of attack and Reynolds number. If we move down below, we have the automotive plot, the side view of accumulated drag versus X. And then if we look at the bottom left corner, that's actually an unsteady case, scramjet combustor. And 4 different variables are being looked at 4 different windows on the FieldView screen. And these can be played interactively, so you can have all the time synchronization and zoom and rotate, etc., with these multiple unsteady cases. And these are all kind of forms of standardized plots in movies. We're going through a transition in terms of computing resource. We're going through the change to cluster computing and different kinds of HPC architectures. And really, that's why I wanted to set us in a historical framework to start with. What's happening to everyone in modeling and simulation is that CPU speed has been generally increasing, although per core speed is actually going down slightly. But essentially your throughput, CPU throughput is increasing. Cost per core is decreasing. Cost and speed of disk, however, is not keeping up. I think everyone knows that. And so you're able to compute more results than you can process if you are dealing with saving and moving around the big results files. And another factor that's happening is that memory per core is also dropping. So these things are cluster side effects. They're architectural decisions now that we've gone down the cluster path. And although we can compute CFD in parallel, the issues that are coming up essentially have a lot to do with what we do with those computed results. So storing and using results file are a key issue, and that's what we're going to talk a lot about today. Clusters are producing results files that can be problematic to store and access. And especially this is true for unsteady CFD, where you might have moderate size files, but thousands of them. You have remote HPC resources where you cannot FTP full solutions back and forth, very large size models, or many calculations in a design space exploration, maybe 10,000. Files are too large for available storage. It takes too long to copy files. Or you might have too many files of a moderate size, and files require too much memory to read in. That is, I want to post-process on a local resource, but it doesn't have enough memory to even deal with the file. And so there are some solutions to all of these things, but the most important one we're going to talk about today is how to use extracts to divide and conquer. We're going to talk today about extracts, taking advantage of extracts. We want to get all that we need from our solutions, but we want to minimize the issues using the large results files. Sounds good, right? So what is an extract? What's this magical thing? Well, it's a file. It's a compact format. It contains all of the numerical and mesh info from your favorite objects, be it surface geometry, cutting planes, isosurfaces, or stream or streak lines. And on each of these objects, you can store many scalars and vectors. So these, I've got a couple of small pictures on the right, a truck example and a takeoff and ascent vehicle, rocket vehicle, and these are made up of extracts. Okay? So the idea is very simple. First, extract what you need from the volume file, and then later post-process the extract that you've taken out. And it seems so trivial and easy, and in fact, it's not an original idea of intelligent light. It was first thought of by Al Globus at NASA Ames, and also carried forward significantly by the famous Robert Hames of MIT. Within our product line, within FieldView, we have extracts which we call XDB files, and the name comes from extract database. They're created in FieldView and now in Visit, either through the GUI or by scripts or FVX, so they can be done interactively or in batch. And the idea is that you read the volume data one time into FieldView, and you write the XDBs, which are subsequently post-processed. But what's the key point about this is you do the reading of the volume data and the creation of the XDB on the HPC resource remotely, where you have a large amount of compute and where the files are local. And then you can bring the smaller XDB files wherever you're actually going to interact with them or finish your work. XDBs are numerically identical to the internal form within FieldView, which means if you do a mass flow integration on a cut in the volume file, it's going to match the mass flow integration on an XDB. You can store your choice of quantities, which are either in the solver file directly or using the function calculator make up quantities, new derived quantities, and store those in the XDB. And the XDB files are hundreds to thousands of times smaller. There's no lossy compression. There's nothing like that. It's simply the fact that the surfaces that make up the things of interest, like an aircraft fuselage or a cutting plane, don't have to carry all the three-dimensional topology of the solver. And, as you all know, many of the cells in the CFD calculation are needed because of the fidelity of the calculation that you're doing. But in the end, if you're interested in forces and moments or mixing fractions, that can usually be derived by a much smaller subset of the number of cells in the data set. So the best way to do this, to talk about this, I think, is by example. So we'll start with a simple example, which is just creating XDBs on an HPC resource and post-processing them locally. So 4 steps. Write the result file in the HPC system like you always do from the solver. With a script, start up FieldView in batch, and using a script, read the file with parallel I/O, which FieldView supports, of course. Use a script to write the XDB files, and while you're at it, you could write some images or animations or system quantities, whatever you'd like to do, and then release the FieldView. You can then move the smaller files to your local location for post-processing. It's very simple, very straightforward. The benefit is smaller memory need on the local system. If you're starting with a 6 gigabyte volume file and you want some cutting planes and your body geometry and maybe a couple of isosurfaces, that's going to be on the order of hundreds of megabytes. And so the memory load on the local workstation is much less. It's faster to get the files across to the local system, even if you're transferring all the way across the world, because they're smaller. It's common sense. And it's much faster to load cases on your local workstation. Lots and lots of benefits. So again, the volume data exists. It's read on the HPC resource, converted to the XDBs, and then only post-processed or touched on the local system. So the big question that always comes up right at this point is, well, if I'm extracting cuts and isos and things, don't I have to limit what I save? And that's a very good point. It's a very good question. It's very valid. So I've got a few perspectives on this. First of all, number one, for many of you, the decisions have already been made on standardized plots or movies. Remember our earlier slides. If you're already using scripts to create standard plots and movies, you add a single line to your script to write XDBs. And now, instead of just getting a plot or a movie, you get a full 3-dimensional extract that you can load into FieldView or XDBview, rotate around, zoom, change variables, do animations, make additional movies and plots. All of that value by just essentially saving the XDB from your standard scripts. Now, using XDBs is usually a trade-off. It's made because of other limits, right? We wouldn't be thinking about saving time or saving space unless it was an issue. So as we saw from our earlier survey, folks are limiting what they can study. If you can remove the limits of what you can study and do more work, perhaps it's a worthy trade-off to simply say, I'm going to focus on these isosurface of Q criteria, these cuts. Hey, I can have a choice of 10 or 20 variables. I can change that later at post-processing time. I'm not really that limited. And number 3, since XDBs are so much smaller than the original volume files, you can make many. You can save many and choose later. So in the auto industry, it's very common to make a slice every 10 centimeters all the way down and across cars. And you have plots of many of these movies. They're reviewed by leafing through PowerPoint. And here's an example where with an XDB, you can change the variables, you can change the color map, and you can pick what slices are important to you after the fact. And in fact, just like in FieldView, where you can sweep a cutting plane through a volume, you can create a sweep XDB and sweep through that during your post-processing phase. So now that I've kind of talked about that issue, let's look at another example, and this one is particularly the unsteady case. So in a loop, for each time step on the HPC system, write the result file, read it into FieldView, and with a script, write the XDBs that you want, geometries, isosurfaces, particle traces, whatever. Then FTP the XDBs to the local post-processing site. It might even be just another disk system within the cluster. It might be a post-processing node, or it might be your desktop. And in the same loop, compress archive, or delete the results file for that time step. So that means that at any given time, you have a couple of time steps around of the full volume file, full size, and you're extracting what you need and then either removing them or reducing their impact by compressing or archiving them. The XDBs are building up at your local site, and you can use them to explore the unsteady results. So instead of just looking at a movie or set of movies, you can rotate, you could zoom, you could change variables. On that earlier picture I showed you, I had the 4 scramjet combustors, 4 different variables, time synchronized, and even the views are synchronized within FieldView as you zoom and move around. So now we have 2 sets of benefits. We have a smaller file allocation on the HPC system, so you stay below that line of IT scrutiny, and you also can now save more time steps and run larger cases, because at any given time you don't need to have all the files around. And then back on the local system, we have our same 3 initial benefits: smaller memory need, faster to get files across, and faster to load cases. But now unsteady data becomes interactive. And the XDBs are so small, you can actually now do side-by-side comparisons of unsteady cases in multiple windows. Before, we would just be looking at movies. So here's an example of that in action. We did this about 5 years ago. 10 billion cell unsteady case using XDBs. This was computed about 10,000 cores on the K computer in Japan. The results came out in a binary plot3D file, multi-zone, so there was 10,000 cores, there were 10,000 zones. The files were on the order of 1 gigabyte per time step. So the visualization server, terabyte. The visualization server had about 900 gigabytes of SSD on it. So this is a key point, by the way, if you're setting up a Viz server, is to have a solid state disk that your compute nodes can load things into for the post-processing. It makes things very, very fast. So we used 256 cores, 256-way parallel FieldView, read the data, did an isosurface, calculating the Laplacian of P. We created an extract XDB of the isosurface, and from start to finish, so starting the read to writing the XDBs, it was 120 seconds per time step. But once we had the XDBs, each time step was 15 megabytes, not gigabytes, megabytes, and it was able to be looked at interactively on a laptop. Example number 3 is a little bit more complicated. It's kind of just to get you to stimulate your imagination, but using XDBs to actually enhance your post-processing workflow by doing things you wouldn't do in other ways. So here we're going to use XDBs to speed up the differencing between cases. So for case number 1, let's say I'm going to compare 2 different card designs. For case number 1, I create an XDB on the cuts and surfaces of interest. Then I read the volume data for case number 2, and I subtract the XDB of case number 1 from the volume data of case number 2. So differencing can be very time consuming if you're actually taking 2 full 3D meshes and subtracting one from the other. But here you're simply dividing and conquering. You've extracted the XDBs first, and you use those later for the differencing operation. So it's smaller memory need for differencing, faster for the subtraction, and because of those 2 things, you can do automated differencing across many variables and cases. So I'm going to change speed now and talk about a different topic, a more state-of-the-art topic called in situ post-processing. And here we're going to essentially extract our XDBs directly from the solver memory as the solver is running. And this in situ technique has been in use for a number of years at scientific research organizations. Department of Energy in the U.S. has been a big proponent of this for many years. And in fact, the reason that Intelligent Light got involved with Visit and LibSim, which is its in situ component, is because it is the workhorse production code for ultra-scale visualization analysis. In an in situ workflow, you instrument the simulation so that it can write out the extracts directly. So we have a module called LibSim, which you integrate into your solver code, and we share the memory of the solver under the direction of scripts and function calls to create the extracts and write the XDB files. So every n iterations, LibSim is called, extracts are created directly from the solver memory, and written to XDBs. So the difficult part here conceptually is that we're going to integrate another library with our solver code. And it's going to work in place, hence the name in situ. It's going to work with the volume data in place, calculating those derived geometries, shape, cutting planes, or isosurfaces, and then do the I/O directly to XDBs. Once you have the XDB file, the XDB workflow is exactly the same as it was from working with files. So you can get started working with files and migrate towards an in situ situation later. The contents of the XDBs are exactly the same, whether they come from Visit or they come from FieldView. And in fact, I should mention that XDBs are fully solver independent. That is, once you have an extract from overflow or a commercial code like star CCM Plus and you're doing subtractions or things like that, FieldView does not care. It's just essentially an extract with variables on it. Now, in situ has another great benefit, which it also saves solver time. And this is frustrating a lot of times to the guys who write and maintain solver codes, because you go through all the work to optimize your solution loop and left-hand, right-hand stuff, but then you're waiting for the I/O to happen every 5 iterations or so. So this is some work we did in conjunction with Jim Forsyth, who's currently working with NAVAIR in the U.S. government for the Create AV Kestrel code. And this is a code we've worked with over a couple of years for instrumenting with Visit. We have some other webinars on this topic that are available, and also published papers at the AIAA and other organizations. If you send an email to info@ialight.com or go to our website, you can find some of those materials, download them, and take a look. So here's some of the recent work they've done. The image on the right shows what's called GT helicopter. It's a notional helicopter. 1,000 core run, write XDB extracts every 5 solver iterations. So it's obviously you can see a geometry and also a Q criterion, ISOs, and you may not be able to see it, but the bottom right corner picture has actually the background grids, the AMR grids in the background. 32 million cells unstructured for the helicopter, 220 million cell AMR for the airflow around it. Now, if the volume data were written every 5 iterations, it would take 30% of the wall clock time. You think about that. That's kind of a representative number, right? So 70% of the time you're actually doing the calculations, and 30% you're doing file I/O. It's that nasty file performance coming back to get you again. We actually instrumented this with in situ. It was done by Brad Whitlock, who's the leader of our team dealing with Visit. And in situ to create these extracts took 3% of the simulation time. So you went from 30% to 3%. And the XDBs were 21 times smaller than the same volume files for the same time steps. So there's an additional benefit to an extract workflow with in situ, which is essentially increasing your solver throughput. So how does somebody get the benefits of in situ? Well, as I said, your solver code needs to be instrumented, that's the term we use, with Visit's LibSim module, which we make available. It's also available by open source download from Department of Energy, Livermore Labs. Actually, NERSC is probably a place. We also have a SVN repo at visit.ialight.com. And some solvers are ready. For example, in the CFD world, Overflow, NASA's Overflow, it's available. You can get a distribution from us for that. That's instrumented. AVF Leslie, which is a reacting flow code. And as I mentioned earlier, Create AV Kestrel. If you have codes that you've developed you want to have instrumented and you want help, that's something we provide. We're very happy to get people going with in situ because we see this as a big trend. And I think that, you know, one of our points in this whole presentation is that the world of CFD is going to kind of change because we can't do anything to make disk access cheaper or faster. So we're suggesting that the extract way of working, and in fact extract plus in situ in the longer term, are going to become more of the standardized ways to do a CFD workflow. And we're very, very interested in helping our customers make that transition. And just as a side note, I mentioned that Brad has worked with some of the largest systems with Visit LibSim. We've done porting and benching 98,000 cores in situ. That's for a single run, single calculation on Sequoia, which is a Blue Gene Q machine. And 130,000 cores we've run up to, actually a little bit more than that, on Titan, which is the Cray at Oak Ridge National Laboratories. So now that I've been talking to you about in situ and talking about FieldView and Visit, there's another thing which I'd like to talk about today, just very briefly, is HPC FieldView. And it's a new product that we've been working on here at Intelligent Light. And we're trying to leverage the best of Visit and FieldView together for people who are doing things at a very large scale and in situ. So HPC FieldView essentially says, take the FieldView client, which you see on the left-hand side of the screen, and give people the choice of either the FieldView server or the Visit engine as a server. So if you're running regular FieldView jobs, HPC FieldView will now run up to 256 cores per data set. And we also have optimized, or actually optimized is not the right word, but we've updated our MPI to be able to take advantage of the local fabric drivers that you have for higher performance. And that's just regular FieldView, but with the ability to go higher performance in terms of the MPI count. If you invoke FieldView with the Visit engine, you get the FieldView client, the FieldView GUI, but with the Visit backend. And Visit brings to us different readers. It brings a lot of different functionality. Visit really is probably the most widely functional code. Some of you might be familiar with ParaView, which was developed more as a demonstration code for parallel rendering and the use of VTK. But Visit has a huge, huge capability in terms of filters and extensibility, and most importantly, scalability, high scalability. So that's now available in FieldView HPC. So you can start FieldView and use the Visit controls to access some of the largest compute servers, say in the DoD and DOE, and process your data using the Visit engine. But all of your graphics and FVX and all the things that you're used to are available through the FieldView GUI. So HPC FieldView provides more specifically the FieldView user experience and automation. And as I mentioned earlier, XDBs can be read by FieldView and they can be written by Visit. So now you're kind of combining both together. You have the Visit engine with all the scalability and HPC host control, and bringing now important readers into the FieldView community, XDMF, HDF5, Chombo, Exodus 2, etc. Visit brings over 100 readers to the game. And here's an interesting thing for people at commercial companies. We distribute the LibSim. We support LibSim at Intelligent Light. We distribute LibSim as part of the HPC FieldView distribution. So instead of an open source download, you're actually getting the pieces that you need from us as part of a commercial distribution. For many companies, the open source download issue is a big problem. There are more things coming. I don't want to spend time on that today. I just wanted to give you a brief overview of what HPC FieldView can provide to you and get you thinking about it because it really represents kind of the next step in our evolution with FieldView. FieldView's evolution has always been driven by data since 1990 when we first released it, when we were looking at standalone visualization, right? Then people started to use more remote compute resources and parallel resources. So we had client server and MPI parallel kind of connected. Client server do part of your processing on one end and part locally, but there was tightly coupled, tightly connected. Then we realized that you can't stay connected for these long sessions, and files are becoming bigger and transient cases are bigger. So we started to get involved more with data management and, of course, XDBs. And I want to point out that everything I've talked about today is available even in the lowest end version of FieldView, the single system, all the way up to our full parallel versions in terms of being able to work with XDBs. You don't have to buy anything extra. If you're a FieldView customer, you already have it. And then now, since 2013, we've been working with in situ, direct extraction from the solver, and FieldView, HPC FieldView is now part of that story. So Intelligent Light is now kind of filled out its product portfolio to be able to help our customers. And the key point is that XDBs, or extracts, are in the center of our universe. Whether it's accessed through FieldView, our primary post-processor, XDBview, which is a free viewer. Some of you are aware of it. It's available from our website. There's no licensing. You're free to send it to other customers and send it with XDBs to share things and publish. Visit, which now is our high-end product for in situ extraction and special purpose post-processing, and also XDBlib, which is a library that can be licensed from us to directly write XDBs from solver codes. So that really brings me to the end of my part of the presentation. I'd like to thank you all very much again for your time and energy in participating with us.